There is a second part to the fundamental theorem of calculus, and the second part poses this question. Is there a way to find the exact accumulation over a closed interval a, b? In other words, if you had a function on a closed interval a, b, is there a way to find this exact accumulation? And the answer is yes. It turns out you just need an antiderivative that's a function, a continuous function on that same closed interval, and take the difference between the higher accumulation minus the lower accumulation. We're going to go ahead and run through the proof of this fundamental theorem. We're basically going to prove this identity. We're going to start with the left-hand side expression, and we'll simply work our way to the right. Proof. Suppose f is a continuous function on a closed interval a to b. By the fundamental theorem of calculus, part 1, we have an antiderivative g of x defined as this integral. Now let f of x be any other antiderivative of lowercase f of x. By one of the consequences of the mean value theorem, we know that antiderivatives differ by a constant. Thus, we can write f of x to equal g of x plus some arbitrary constant. By properties of integrals, we have the following observation. Start with capital F of b minus f of a. We're going to substitute and write this in terms of the lowercase g function. Notice you could simplify with algebra, and you can see that c minus c will get you 0. You are now left with an expression g of b minus g of a. But g of b minus g of a is simply this substitution evaluated at b. So we get this first integral, and the second integral is g of a. G of a is the definite integral from a to a of f of t dt. We know from properties of integrals that is simply 0. Now we're left with the integral from a to b f of t times dt, which is what we were looking for. By the transitive property of equality, we know that f of b minus f of a is equal to this definite integral. Equality is symmetric, so we could write the definite integral is now equal to the difference of these accumulation values. We're going to use the fundamental theorem of calculus part 2 to evaluate the following integrals. We are going to need some new notation to make things a little bit clearer. Make sure you know your antiderivatives. Got to remember your antiderivative of 1 over x. Now the fundamental theorem of calculus part 2 says if you have this, then we could actually find the exact value by using this difference of accumulations. The way I usually write this is I actually introduce a bracket notation. I prefer a bracket notation because of situations where there's a constant in front of the function. And if there's a constant in front of the function, the bracket notation will come in handy. This expression here is going to have the same value as the antiderivative of 1 over x. And then I'm going to use a bracket. I'm going to write my domain at the end of that bracket. So we're going to evaluate this from 2 to 5. This is the difference of two accumulation values, namely the antiderivative evaluated at the higher value minus the antiderivative evaluated at the lower value. Notice the expression is simplified. Do a similar process for the next example. Notice once again, I use a bracket notation. Now here's a great example of where the bracket notation can really help you understand that we could take advantage of the bracket here. And we have a greatest common factor. The greatest common factor is 3/4. And I could actually factor out the 3/4 from our bracket notation. And now we could evaluate from 1 to 8. What we have is 16 minus 1. And so this is 45 over 4. Once again, we simply simplified an expression. We really didn't solve anything. We just wrote a lot of substitutions. Antiderivative of cosine of theta is actually simply the sine of theta. And remember, you have your trig values of your common functions with common angles memorized. So that way you have no reason to use a calculator. This is 1 plus 1, which is the final expression of 2. Once again, you simply substitute it over and over again and simplified an expression. The antiderivative for this next function is the opposite of secant of theta. And I'm still going to use the bracket notation. Notice I factored out the -1 from the bracket already, and that will easily allow me to find a difference of the accumulation values. Make sure you have your trig values memorized. So final expression is 1 minus the square root of 2. Notice the first expression simplified to 1 minus the square root of 2. We'll continue to simplify expressions using the Fundamental Theorem of Calculus Part 2. I like the bracket notation because it allows me to take out the greatest common factor. The greatest common factor here is 4. And now I could actually take the difference of accumulation values on the domain from 0 to 1. And of course, you have your trig values memorized. And the answer here is pi. The first expression simplified to the final expression of pi. The next example requires you to remember your knowledge from trigonometry. First thing I'm going to do is actually respond to it with algebra. We're going to factor the numerator and seek a substitution. Notice we used a very convenient identity, and now we're left to find an antiderivative for the sine of theta. That will be the opposite of cosine of theta, evaluated from 0 to pi over 3. Once again, I could actually factor out the greatest common factor, and I could evaluate the cosine of pi over 3 minus the cosine of 0. You have your trig values memorized, and that way you could keep writing and keep evaluating without hesitation. The final expression is 1/2. Explain what is incorrect about the following equation. Well, you're given a function 4 over x to the third power is not continuous at x equals 0, which is in our restricted domain. -1 to 2. Thus, we cannot apply the fundamental theorem of calculus part 2, and this equation is very false. Can you draw a picture that represents the natural log of 5? Now, if you don't want to see the answer, make sure you pause the video and look away. After giving this some thought, and you still haven't figured out the picture of the natural log of 5, go ahead and play the video. The accumulation here represents the natural log of 5.